Since we're linking linear transformations to matrices anyway, let's have a look at why matrix-matrix multiplication is defined in the funny way that it is. Okay, so what if we have two linear transformations? We have linear transformation A that takes vectors from CK into CM, and we have a second linear transformation that takes vectors from Cn into Ck. Now, given the vector x in Cn, we could first apply the linear transformation LB to this, and notice that that results in a vector of size k. And then we can take that result and we can feed it into our linear transformation LA to yield a vector of size m. What is that called? It's called composing functions, right? So we can compose LB with LA. All right, now, if LA is a linear transformation and LB is a linear transformation, then you can prove that the linear transformation defined by composing these two is itself a linear transformation. All right? So, what does that mean? We just learned that this linear transformation can be represented by a matrix. Let's call it A. And notice that that matrix would have k rows and m columns, m rows and k columns. Okay. And then we can have a matrix B that can be represented by a k by n two-dimensional array matrix. And notice then that there should be a matrix that represents LC, let's call it C. That takes as input a vector of size n, and that gives as output a vector of size m, so it would be an m by n matrix. And notice that C applied to a vector x must be equal to first applying b to that vector x and then taking the result of that and applying a to that. Okay. Now, you can say C is the matrix that represents the result of first applying b and then applying a. And therefore we can say, let's define C equal to a times b, where C is the matrix that captures the net result of composing A and B. All right? Now, what did we just learn? We just learned that the columns of the matrix that represents a linear transformation can be created, can be computed by plugging in the standard basis vectors. So, the jth column of matrix C should be equal to LC applied to the jth standard basis vector, which then is equal to the composition of these two. Now, if you put in the jth standard basis vector and you evaluate LB, what do you get? You get the jth column of matrix B. So this here is equal to LA applied to the jth column of matrix B. And how can we represent LA applied to the jth column of B? That is just matrix A times the jth column of B as a vector. Okay, so what do we learn? If we take C and we compute it as A times B, then you can think of C as consisting of its columns There are n of those. And that you can then think of as A times B, but now we can partition B by its columns. And what this now tells us is that the jth column of multiplying A times B is just A times the jth column of B. So this here is just a matrix where the first column is A times B0, the second column is A times B1, and the final column is A times B n minus 1. Now, that may not be how you were introduced to matrix-matrix multiplication, but if you think about it very carefully, you find that how you compute entries of this matrix is exactly the same, or at least yields exactly the same result as the formula that you were taught.